I'm going to try to keep it not too much over 30 minutes, and that way we will have some time for questions. So we are going to see what is on tap today. It's, let's see, this is a little bit about my background. I've been a member of different technical committees through the years, and this is a disclaimer. I'm speaking as an individual and not giving an official position or interpretation of any of the committees that I'm a member of. So this is my opinion. And if I get some hard questions, it's just an opinion. So we are going to cover the common UL low voltage fuse standards, current limitation conceptually, and the different regions of the time current curve. That is the time delay portion, the no time delay portion, and the current limitation portion of the time current curve. And we are going to touch on medium voltage fusing to reduce arc flash. I think we will be successful in recording this presentation, so the slides hopefully will be available so you don't have to take great notes, but that's the plan. So we are going to start with common UL fuse types, and we are going to do some comparisons of the common ones. The low voltage fuses most commonly in play are the code fuses, code dimensions, like class H, class K, class RK, class J, and class L, and class CC. Those are the most common ones. And if you are dealing with the end user who has a lot of old fuses, I'm going to give some reasons why you should encourage them to go to the most modern fuse, the RK1 fuse, instead of the older versions. So physically, these are what the UL fuse dimensions are. When we think of engineering and having the correct fuse, the fuse characteristics that are most important are the ampere ratings, voltage ratings, interrupting ratings, time delay or not, degree of current limitation, and we are going to really get into current limitation in this talk, mechanical dimensions, and manufacturer. Coming back to the first one, ampere rating, generally you don't want to load the fuse over 80%. There are some exceptions, but generally you don't do that. If you have motor circuits, normally the motor circuits use the fuses for short circuit or ground fault protection, not overload protection. And they are sized higher, maybe 175% of the motor full current. With the voltage rating, if you have a low voltage fuse, as long as the fuse is at least as high as the voltage that it has to interrupt, it's a good application for the voltages. For instance, you could have a DC voltage rating, AC voltage rating, a combination of both. The next thing is interrupting rating. We are not going to go into that in this talk, but it's very similar to interrupting rating on a circuit breaker or a CCR rating of a switchboard or something like that. Time delay or not, that we will get into that in the time delay portion or band of the time current curve, time delay or not. And we are going to really get into degree of current limitation in this talk. Not so much the mechanical dimensions or the manufacturer. We are going to try to keep the advertising down to a bare minimum. So this is a condensed UL fuse class comparison. The H on the left is an old style that's been around for quite some time, and the UL requirements to get a fuse listed in the class H are not very hard. The interrupting rating is only 10,000 amps, and there is no current limitation, and the overload region is up to 10 times the nominal amp rating of the fuse. And the non-time delay region is generally over 10 times the fuse rating. It has no current limitation. Going forward in time, the K5 fuse has a 50,000 amps interrupting rating, and the current limiting region is defined by UL. It has to cut in at 65 times the amp rating. So if you had a 1 amp fuse, it should cut in with 65 amps. It's not a hard and fast rule, but if you have a 30 amp fuse, 30 times 65, that's when UL would require the current limitation begin. And we will review that in depth in some other slides later. RK5 is the most common fuse actually used, not new installations, but actually used in fuse clips today. And it has 200K interrupting rating, has some current limitation, and it still has the 65 times the amp rating to begin current limitation. And a typical part number would be TRSR. The next one, and the last three are shown in red. Those are current fuse types that are recommended. RK1 has the same dimensions, or will fit into the standard fuse clips of the H fuse clips, K5 and RK5, in the same dimension. If we go back a couple of slides, you can see that this is an example of an RK1 fuse. It will fit into an RK5, K5, or Class H set of fuse clips. So the only difference is really the current limitation and the modern design, but it will fit into the same fuse clips. This has current limiting region starting at 30 times the fuse's rating. And Class J is very similar, but Class J has different dimensions. It's a smaller dimensions. We are going to go back to the prior slide. This is an example of a Class J. This is a 30 amp. All these are 30 amps. So you can see the Class J is a lot smaller. And sometimes it's preferable in OEM panels, specialty panels, but in the power distribution disconnect switches, they have enough room. They generally go to the classic design. So in the recommended fuses, if it's a modern panel, not a power distribution panel, but a control panel, you would often see Class J fuses. If it's a new fusible panel for power distribution, RK1 is the favorite UL type. Class L generally is applied at over 600 amps. UL has modified their standard to allow lower amp ratings down to 100, say, but it's still in the 800 amp size mechanically. That means that it will bolt into an 800 amp switch. So this is the overview of common UL fuse class comparisons. This is a typical RK5 time delay fuse, and you can notice that it's made up of two segments. This segment is a short circuit element, and this short circuit element will be the provider of the current limitations, such as it is in the RK5, and this is the overload element. It's an electromechanical spring-loaded device that will measure the current, and when it's persistently above the fuse rating, it will snap back and open the circuit. And characteristically, and I'm rounding off for the sake of simplicity, the overload segment will activate at 10 times or less the fuse's rating. And more than that, more than 10 times the fuse's rating, the short circuit strip will open without any time delay. So the process is they are wired in series, and when they are wired in series, if you have either section open, the fuse is open, it's non-resettable, and you throw it away and replace it with a factory fresh calibrated unit. With this, we have the best of both worlds, because this is sized maybe 10 times the fuse's rating with no intentional time delay, and this is calibrated to the fuse's rating. As a result, if you have a overload, this will open this section, and if you have a short circuit, this will open without any time delay. Well, when we say time delay, we are talking about seconds. When we are talking about short circuit instantaneous, we are talking about fractions of a cycle. And let's see the difference between an RK1. RK1 is a more modern design. It has a more compact time delay mechanism. It has special alloys in the short circuit strip, including a lot of silver. And the way it works is that if you have a short circuit, it will melt the weak links here and melt the silica sand in it, and the silica sand will turn to glass, molten glass, sometimes called fulgurates, and it will have a high resistance. The amazing thing about this is not time dependent. If you are having an electromagnetic assembly like this, or even a circuit breaker, it has inertia and springs and time that's going to delay the actual opening of the circuit. With this, it's only dependent upon the current. If you have more current, it will operate faster, because if it melts the silica sand, it will turn to glass, and it's very high resistance, and it will open the circuit. Well, we are going to try to get into current limitation and gain you a good concept of current limitation. Well, the definition from the National Electrical Code 240.2 is, and this is an official definition, I'm going to read it, but you would have to think about it because it's kind of a legal document. A device that, when interrupting currents in its current limiting range, reduces the current flowing in the faulted circuit to a magnitude substantially less than attainable in the same circuit if the device were replaced with a solid conductor having comparable impedance. So that's in the first half cycle. If you think of a sine wave, the first loop, it will reduce it down compared to a bus bar with the same impedance. And we saw previously how that's possible. And tying it to arc flash, the incident energy resulting from an arc flash is proportional to I squared times T. And we have some data from testing fuses regarding I squared T. That's the incident energy, or proportional to the incident energy that can be let through a fuse under a short circuit. For instance, if you have low currents and you have the time delay action of the fuse controlling the current instead of the short circuit link, because of the duration of the time, you can actually have more incident energy than a quick spike. And we will explore that a little bit more. But the overall fuse mitigation strategy is to reduce energy by properly applied current limiting fuses. And it's most effective when you have an application when the fault levels are high. Generally, we think of fault levels when they are higher are bad. Unfortunately, we have a silver lining. If the fault levels are high, fuses can be very, very effective in reducing incident energy. So let's look at a waveform here. We have the red line indicating the current going through the fuse. If we extend that a little bit, the fuse will cut off the current provided that it's in the current limiting range, and bring the current down so that it's completed clearing by the first half cycle. And according to the definition from the National Electrical Code, it has substantially reduced the current flowing in the first half cycle. Now, replacing that with some UL classifications, you can see that Class J and UL Class RK1 are very similar. The J's a little bit better, but only incrementally. Class RK5 is substantially worse. It lets a lot more current through it. And if you think of the I squared T, which we measure with UL and fuse categories, the area under the curve is proportional to the I squared T let through of the fuse. So you can see the J and RK1 have a small triangle of I squared T. The RK5 has a large triangle. In fact, with the UL standards, UL 248, in a 100 amp class RK5 fuse, it allows up to a maximum of 50,000 I²T. With the same rating, 100 amps, the UL classification RK1 limits it down to 10,000 amps. So in a fault condition, if you have a RK5 fuse and you replace it with an RK1 fuse, you will have a 80% reduction in I²T. Well, let's look at the regions of the fuse time current curve. We are going to see the time delay region, no intentional time delay region, and the current limitation region. This is a comparison of a 100 amp RK1 and a 100 amp RK5. And we can see the current scale here. It's in amps, and because we have a 100 amp fuse, 10 times 100 is 1,000 amps, so we have placed an arrow here. And to the left of this is the time delay region. And if you think of a typical application, if you have a fuse that's not more than 80% of the continuous rating of the circuit, or if you are using it for motors, use sizes approximately 175% of the motor full load current, and the motor full load current is related to the inrush current of maybe 7 times. So if you have a motor circuit, properly applied fuse of 100 amps, maybe we'll have an inrush of 500 amps, 2, 3, 4, 5. So this is the inrush, and this is the critical part for most motor applications. And you can see the RK1 and RK5 are almost identical with the time current curve. I assume that you have a lot of experience with time current curves. This is time in seconds. And so with this, you can see if we have higher amounts of current, maybe 2,000 amps, there is quite a bit of difference. Actually, at the 1,000 amps, we can see some substantial differences, 0.2 seconds versus maybe 0.8 seconds. So it diverges there. But the important concept is this is where the time delay is critical for the loads, and after 10 times it's not critical. There's no intentional time delay. So now we have the transition to current limitation. I have set up a 200 amp RK1 and a 200 amp RK5. They are pretty much identical if we look at the two fuse curves, but one, the UL standard says it has to go into current limitation, and this is from UL 248 for an RK1 fuse at 30 times the full load current rating. So if we observe over here, 200 amp fuse times 30 is 6,000 amps. At 6,000 amps, this yellow-orange fuse curve has to go into current limitation to be a UL listed fuse per UL RK1. So the red curve, however, is a RK5 fuse, and the RK5 fuse per UL standard 248 says you don't have to have this RK5 fuse go into current limitation until 65 times its ampere rating. So that's 13,000, which is indicated on this. So you can see the requirements are quite liberal for RK5 fuses and more strict on RK1, similarly for Class J. So from to the right, it's current limitation. To the left was no intentional time delay, and way to the left was time delay. So those are the three sections. Now this is a fuse curve from IEEE 1584 standard, and they are presenting it. One axis, this horizontal axis, is bolted fault current in thousands of amps, and the vertical axis is incident energy in calories per centimeter squared. The fuse, this is a UL fuse. It's not a part number of designated as a part number of any manufacturer. It's RK1 200. So if we see that 5, maybe 3,000 amps, 3,000 amps or less, the incident energy will be real low, has a category 0. However, if the current is so low that it fails to melt the short circuit strip right away, it will be in time delay, and time delay will let the circuit cook, and it will have a lot more combined incident energy. But the important point here is if you have high available fault current, it will have low incident energy. So it would be a good application if you had high available fault current for protection. This is the circuit breaker equation from IEEE 1584. Notice it has the same shape on the left here. This is indicative of the instantaneous trip. If you have enough current to have the instantaneous trip, it goes down to a low value. Typically it would be 10 times, 12 times the full load rating of the circuit breaker. But contrary to the fuse characteristic, because the circuit breaker has a fixed time and the current goes up, remember the I squared T, if T holds constant and I goes up with a square, you will get this phenomena, and the more available fault current that you have, the incident energy will go up because it's a fixed time device. This is a tested out graph, and it's also conforming with the IEEE 1584 2002 equations. We have compared two devices. This is a Class J fuse 200, and this is a non-time delay fuse like a Class H that has been has had the renewable links replaced so that it won't interrupt for 6 cycles, or it could be representative of a circuit breaker, a main circuit breaker that has a 6-cycle intentional time delay for coordination. The contrast here is the red line at 20,000 amps available fault current, is flat all the way up 65,000 actually would be extended up to its maximum interrupting rating. With a fixed 6-cycle delay, with a circuit breaker with a fixed 6-cycle, the incident energy would go up with the available fault current. One of the design examples would be a 600-volt motor control center. We have a special fuse, A4BQ800. Many times this is current limiting enough to have the entire motor control center, if the motor control center is fed upstream by this fuse, to hazard category 0. This is a graph that shows incident energy versus minimum voltage fault current. I'm going to caution you that this is a tested result at 600 volts. It's not applicable to a 480-volt system. It's not applicable to a 208-volt system. This is applicable to a 600-volt system only. So this red one is a 800-amp fuse, one of my most current limiting Class L fuses. And incidentally, we have many types of Class L fuses. So if we have 20,000 available voltage fault current, the actual arc flash will create enough current going through the fuse to bump it into the current limitation mode, and it will be hazard category 0 downstream of this fuse. And the transition is between 15 and 20, but it's 600 volts, and 480 volts, 208 volts are different. And you can see is the fuse goes up like a 1,000 amp fuse, it's less current limiting because the current limitation is proportional to the nominal rating of the fuse. If we go up to a 1,200 amp fuse, it's still higher. But if you get to have a higher available fault current, it will have the limitation that you want hazard category 0. We are running out of time, but I'm mentioning that we have several different types of Class L fuses, and the Class L fuses are in the library of EasyPower. And you can see these are two 800 amp fuses. They are meeting the requirements of UL for 30 times in this category, but one is more current limiting than the other, but they are both meeting the UL standard. One of the suggestions is that if you are doing a study, if you can encourage them to upgrade to RK1 fuses before you gather all the data, you can improve the let-through performance and easily match up the characteristic without opening up all the enclosures to verify it. Part 4, we are going to rush a little bit. Primary fuse selection to mitigate secondary incident energy. The concept is if you have a primary fuse installation, sometimes the secondary you have a lot of high incident energy, and you have problems. This is an actual example. This particular paper mill didn't have a secondary main, and is still allowed by the code if you have a supervised installation and someone wants to cut corners. We don't recommend it, but there are a lot of installations like this. This is a 1000 kVA or 1 MVA transformer at 13.8 down to 480 volts. The arc flash danger was 73 calories per centimeter squared. And using the fuses, the existing fuses, the maximum worst case incident energy was 73 cals. Now this is the time current curve for the original primary fuse, and we have developed various fuse curves that still meet other application requirements, but are size lower or more inverse time characteristics that will reduce the arc flash. I don't want to get into today selecting fuses for transformers. It's involved, but I'm going to list some things that you have to consider before you change the fuse rating or the fuse characteristics. System considerations, transformer characteristics, NEC requirements, and fuse characteristics. These are the system considerations. The transformer characteristics. You don't want to have a inrush of the transformer that's going to damage the fuse and have a nuisance fuse openings. You want to protect the transformer according to ANSI C57.109. You want to have adequate full load current capability and so forth. The National Electrical Code has requirements for the maximum fuse size, adequate interrupting rating, adequate voltage rating, and some of the cabling. Fuse characteristics, ANSI IEEE C37 specifies and covers the characteristics. So in this case, we have the original fuse 9F62DDD080. It's an 80E fuse. And this fuse has a more inverse characteristic, and it will operate quicker in the time delay region. Other considerations, even if a new fuse is great electrically, it still has to fit in to the space, and sometimes you have to modify or replace the fuse clips. This is an overall diagram. This is showing the ADE 9F60 HMH fuse, and it has to be coordinated with all the requirements. Now, the final result is 11 calories per centimeter squared, brought down from 73 calories per centimeter squared. It's not as a category 0, but it's substantially lower, and someone could safely work on it with the proper equipment and proper authorization. So we have brushed over UL low voltage fuse standards for the most common fuses, and current limitation, regions of time current curve, medium voltage. We had a let's see, a question mailed in before the seminar started, I would like to find out if cable protectors can be used on the secondary side of transformers such to lower the incident energy available on the line side of the secondary main disconnecting device. Yes, this is an example of a cable protector time current curve. And the time current curve can be used to calculate the results. If we consider 250 MCM cable protector, and if it's 1500 amps arc fault current, not available fault current, but arc current going through it, it will be 10 seconds. So if it's less than 1500 amps in this particular case, 250 MCM cable protector, it won't be of any reasonable help. However, if you have 6,000 amps, you could go to this curve and find out that's 0.05 seconds to open. And you could plug it in as an opening time, and you will have significantly less incident energy with the that current. If you have more questions, we have a lot of information on our website, ep.mersen, MERSEN.com, and you can search on resources and a lot of information like that. So I'm going to stop recording and see what we have for additional questions.